Hello and welcome to the first clinical immunology tutorial. Tonight's tutorial will focus on introducing you to the cells of the immune system and the organs involved in the immune response. By the end of it, you should be able to understand the main function of the immune system. Also, you should understand the basic organization of the immune system, and you should understand the role of the cells and the organs involved in the immune response. You should also be able to distinguish between the innate and the adaptive immune response. So before we delve into the specifics of the immune system, I'll give you a little bit of history. So in 430 BC, Thucydides noticed that individuals that recovered from the plague had the ability to treat those suffering from the plague. And this is the first hint that we get from history that humans began to appreciate adaptive immunity. But it wasn't until the 15th century that the first crude vaccine was attempted. Clinicians purposely exposed people to smallpox. Over 200 years later, Edward Jenner refined this method and generated the first vaccine, which protected against smallpox. Shortly after that, Louis Pasteur managed to increase the shelf life of food through applying high heat for short bursts of times, and this kills pathogens, and we call this pasteurization. But arguably the most important discovery in the history of medicine, not just immunology, in 1929, Alexander Fleming discovered that penicillin actually combats bacterial infections. So he discovered penicillin. Okay, so hopefully this is a bit of a refresher for most of you. The immune's primary function is to protect the host from infectious diseases, and I've provided you with some images of examples of that. So on the left is cells that has been infected with HIV. In the center is a bacterium that causes tuberculosis, and on the right some red blood cells that has been infected with a parasite that causes malaria. So these are the three biggest killers worldwide in terms of infectious diseases, along with influenza as well. So the immune system also promotes wound healing, as well as removing abnormal cells such as cancer cells. And the final function of the immune system is one that is unwanted. Immune cells can cause disease, namely autoimmune diseases, and also they're involved in allergic reactions as well. So the four types of infection that the immune system will encounter are a viral infection, and an example of that is influenza, a parasitic infection, and we often refer to these as worms, and an example of that would be a plasmodium, which causes malaria, a fungal infection, such as athlete's foot or any type of yeast infection, and finally a bacterial infection. Throughout the module we will refer to these infections as infections, pathogens, microbes, antigens and non-self, and all of these terms amount to the same thing, something that generates an immune response. So this diagram depicts the main cells of the immune system, and we can categorize them in a number of ways. This often confuses students because each cell might fit into more than one category, because each cell has more than one function. Immune cells are created in the bone marrow through a process known as hematopoiesis, and as you can see, all immune cells are derived from stem cells. The stem cell either differentiates into a myeloid progenitor or a lymphoid cell, also known as a lymphoid progenitor. A myeloid progenitor can differentiate into any one of these granulocytes. What isn't shown is that the myeloid progenitor can also become a platelet or a red blood cell. So over the other side of the diagram now, the lymphocyte progenitor can become a lymphocyte. But more accurately, it differentiates into a lymphoblast first. And this lymphoblast then can become a T cell, or a T lymphocyte, or a B cell, or a B lymphocyte. And finally, a natural killer cell. So broadly speaking, we can group these cells into some categories to help us understand what they do. We have the sentinel cells, and They lie in wait inside tissue, waiting for an infection to come along. The three cells that carry out this function are the dendritic cell, the macrophage, and the mast cell. So these cells that are sitting in the tissue waiting for an infection, when they find one, they call out for help from their friends, which are circulating around in the bloodstream. And these cells that circulate have the job of killing and essentially eating cells, and we call them as circulating cells. The third group is the lymphocytes, and these cells are very specific in the pathogens that they target. Morphologically, the natural killer cell fits nicely in with lymphocytes, but in terms of function, it could probably be placed in with the circulating cells, because that's similar to what it does, it circulates. So this is a more accurate and detailed diagram of hematopoiesis, and it includes the cell lineages. So the diagram shows the lymphocytes on the left hand side of the diagram, and it also includes the platelets and the red blood cells that I mentioned before. And note that there are a number of steps that may have been left out from the previous simplistic diagram. On the right hand side we have the generation of the lymphocyte, and you can see following the stem cell differentiates into a lymphoid progenitor, and then a lymphoblast, and then a pre-lymphocyte, and then it decides whether to become a T lymphocyte or a B lymphocyte. Natural killer cells are left off of this diagram. So a more useful way to categorize the cells of the immune system are into those that are involved in the innate immunity, also known as the natural immunity, and those that are involved in adaptive immunity, also known as acquired immunity. The innate immune cells respond rapidly to the presence of something that shouldn't be there, so a pathogen or microbe. The innate cells comprise of the granulocytes, of course, the mast cells, the dendritic cells, the macrophages, natural killer cells, and the complement proteins as well, which we will talk a little bit about later. The adaptive cells consist of both the B and the T lymphocytes, and also these antibodies that come from the lymphocytes as well. The adaptive response is much slower than the innate response, but it's very specific. And we actually have an entire lecture on the adaptive immunity and one on the innate immunity as well. Before we delve into each immune cell, there are some terms I want to introduce you to. The first is phagocytosis. This is the process of engulfing an antigen or a dead cell or even cell debris. The cells that do this are the neutrophils, macrophages, mast cells, and dendritic cells, and collectively they're known as phagocytes. And it might help you to think of them as little Pac-Man-like cells, because that's essentially what they're doing. They're circulating around and engulfing or eating microbes. Cells that are infected emit chemical signals that attract these phagocytes to the site of infection. When the phagocyte comes in contact with the microbe, receptors on the phagocyte surface bind to the microbe. The microbe is then engulfed. The microbe is ultimately discharged as waste materials, some of which is actually used by the host. So we recycle some of these waste materials. So that's phagocytosis in layman's terms. And during the next week's lecture material, or week 2's lecture material, the innate system, you'll go over it in a lot more detail. So I'll now explain it in a way that you would explain it under exam conditions. When the neutrophil arrives at the site of an infection, it will combine with the microbe. Once it is bound, the neutrophil will consume the microbe, forming an early phagosome. The phagosome fuses with an endosome, which has some protein pumps. Proton, not protein. These proton pumps enable the phagosome to become acidified, and this is an important feature because in order for the enzymes to become active in the phagosome, it must reach a low pH. Then a molecule called EEA1 encourages the phagosome and the lysosome to come together. They then fuse together to form the phagolysosome. The lysosome brings with it a range of enzymes that help to degrade the pathogen. So the pathogen is degraded inside the phagolysosome, and the material that is indigestible is discarded. Another concept that it's imperative that you understand is antigen presentation. Almost all cells of the immune system can present antigen, but the cells that do it most often and best are the macrophages, the B cells, and the dendritic cells. Antigen presentation is a straightforward process. Antigens are taken inside the immune cell, similar to phagocytosis. The antigen is then degraded into smaller fragments and displayed on the major histocompatibility complex, or MHC. The antigen is then recognized by a T cell. So very briefly, because I mentioned it on the last slide, the MHC, or major histocompatibility, is a set of cell surface proteins, and they bind to the antigens that have been engulfed by the cell. And the MHCs present the antigen on the cell surface. But the MHC also determines the compatibility of donors for organ transplant. Sometimes we refer to the MHC as the human leukocyte antigen, or HLA. We can divide them into MHC1 and MHC2, which you will definitely hear much more about in the later lecture material. So moving on to the various cells of the immune system, firstly we start with the granulocytes. Neutrophils are the most abundant white blood cell. So circulating white blood cells can be up to 70% neutrophil. Neutrophils are the first responders to all infections, but their primary function is to defend against bacterial and fungal infections. Neutrophils identify their targets and phagocytose them. And neutrophils are a large component of pus that oozes from wounds. They have actually got a relatively short lifespan as well. They'll typically die after they've phagocytosed a small number of pathogens. So moving on to eosinophils, only 2 to 4% of total white blood cells are eosinophils. However, this percentage does fluctuate based on the presence of pathogens or diseases, particularly diseases related to the spleen. The majority of eosinophils can be found in mucous membranes within respiratory, digestive, and lower urinary tracts. So the main job of the eosinophil is to defend us against parasitic infections, worms essentially, and also eosinophils can be found at the site of allergic reactions as well. So eosinophils, like all granulocytes, will secrete chemicals that destroy their targets. Eosinophils deal with quite large parasites, and as such they'll secrete chemicals that break down the parasite. And because the parasite's been broken down, it's a lot more manageable by phagocytes that are circulating around. So the final granulocyte is the basophil, which acts by releasing histamine, and this causes dilation of blood vessels. Only about 0.5% of total white blood cells are basophils, and this makes basophils the rarest immune cell of all. Now, despite the image in the top right corner being yellow, basophils are actually blue, and this is because the granules inside of them are a dark violet colour. So, in terms of size, monocytes are the largest immune cell, and just like the neutrophil, they are a phagocyte, but they have a much longer lifespan than the neutrophil. Monocytes are also antigen presenting cells, so they're quite useful. They are a phagocyte and they're an antigen presenting cell. So they will present pieces of engulfed pathogens to T cells, and this generates an antibody response. Monocytes will remove intracellular debris, and they'll leave the bloodstream and they'll take their contents, i.e. the intracellular debris, to the lymphatic system where they'll be dealt with by the T cells. A macrophage comes from the monocyte cell lineage, and as such it has some of the same functions as a macrophage. It phagocytoses and it degrades pathogens and it presents antigens. But it also secretes growth factors and chemotactic molecules. And chemotactic molecules are molecules that recruit other immune cells to the site of infection. Dendritic cells, they get their name from the presence of these long dendrites, as you can see in the image on the bottom right hand corner. But they also come from the monocyte lineage, and as such they're a phagocyte and an antigen presenting cell. But they also have another function. They heavily influence T cell differentiation. The dendritic cell presents antigen to naive T cells. So I can't reiterate this enough. Naive T cells are cells that have not been exposed to an antigen before. The dendritic cell then stimulates the naive T cell to secrete a particular cytokine. So if IL-12 is the cytokine that has been secreted, then the naive T cell will differentiate into a Th1 T cell. Whilst if IL-4 has been secreted, then it differentiates into a Th2 cell. IL-10 causes it to differentiate into a Treg cell, whilst IL-6 and a couple of others causes it to become a Th17 cell. And we're just introducing you to these terms tonight. At a later lecture, we'll go into a lot more detail on these. Lymphocytes are very much part of the adaptive immune response. There's three types. There's the B lymphocyte, the T lymphocyte, and the natural killer cell. The most distinctive function of the B and T cells is that they produce antibodies. These antibodies are highly specific. They bind to pathogens, they stop the pathogens from invading cells, and they ultimately enhance the destruction of the pathogens. There are many types of T cells, as I alluded to on the last slide, and the two categories that I'll mention on this slide are the helper T cell and the cytotoxic T cell. In short, cytotoxic T cells kill virally infected cells, whilst helper T cells activate other cells such as B cells and macrophages. We can further classify helper T cells based upon what markers are on their surface. If they have the CD4 marker, then they'll bind to an MHC2 on antigen presenting cells. But if they have a CD8 marker on their surface, then they'll bind to an MHC1 on antigen presenting cells. So as I said before, a lymphocyte that has not encountered antigen is known as a naive lymphocyte. And only a small amount of lymphocytes are naive. The naive lymphocytes will circulate between the blood and the lymphatic system. And we'll talk about the lymphatic system soon. When a naive lymphocyte first encounters a pathogen, it stops in the lymphoid tissue and proliferates and differentiates into an effector cell. We will cover effector cells as well, also in another lecture. So the natural killer cells are the third lineage of the lymphoid cell, but their function is a lot different. They are part of the innate system largely, not the adaptive system like the B and T cells. They circulate in the blood, whilst the B and T cells mostly do not. Their main role is to recognize and kill abnormal cells, such as tumour cells, but they're actually very good at killing virally infected cells as well. So that's probably 9 or 10 slides on cells of the immune system. I don't expect you now to be an expert in these. It is important that you read all of the lecture material available in this module, attend these tutorials, and also do your own reading. The more that you read, the more that you will understand. You're certainly not expected to be an expert now at this point. So we could have easily done an entire tutorial on complements. It's an integral part of the immune system, And as part of this module, you must learn as much about it as possible. In a nutshell, complement is a series of proteins and glycoproteins that interact with each other. And they do this to enhance antibodies and phagocytes, removing pathogens and dead cells. That's why you call it a complement, because it complements antibodies and phagocytes. So there's three main pathways, and they all have the same aim: to attack pathogens' cell membranes. The first line of defense against pathogens includes the skin, the mucous membranes, and the secretions from these membranes, also normal flora that's present in the gastrointestinal tract. So, if a pathogen navigates its way through the first line of defense, which it does daily, then the innate immune system is initiated, and this includes the generation of an inflammatory response and the group of proteins that we've just described, complement. And the inflammatory response and the complement will help the innate cells to destroy the pathogen. But we also begin to secrete antimicrobial substances such as interferon, and these are especially effective against viral infections that have managed to get themselves through the first line of defense. So this is an immediate, non-specific defense, whilst the third line of defense is highly specific, and it's known as the adaptive or the acquired response. And this primarily involves lymphocytes, but it also utilizes some of the innate cells as well. The innate system's ability to defend us from pathogens is dictated by genetics. The main aim of the innate immune system is to distinguish between self and non-self. And it does this by recognizing molecules called pathogen-associated molecular patterns, or PAMPs. And PAMPs are molecules that are found on the cell surface of non-self, or pathogens or microbes. So the diagram on the right shows some more components of the first line of defense, some of which are external, including the tears in the skin. We can divide some of the first line of defense into a physical barrier and a chemical barrier. A good example of a chemical first line of defense barrier is the stomach, as this contains gastric fluids with a very low pH, and these can actually just kill microbes. The airways are lined with mucous membranes, and these are a good physical defense, and these trap unwanted pathogens. Another physical barrier on the first line of defense is the epithelial lining, particularly in the airways. The epithelium acts as a buffer between the outside environment and the internal tissues. In terms of a time frame, the innate immune system is stimulated immediately when a pathogen bypasses the first line of defense. The immune cells have pattern recognition receptors, PRRs, on their surface, and through these they recognize PAMPs. So over the next 12 hours, the innate immune cells will attempt to dispose of the invading pathogens using a combination of methods including inflammation and phagocytosis. After 12 hours or so, the adaptive immune system is ready to begin its defensive against pathogens. Many commonly encountered viral infections will be eradicated in less than 7 days or so, and this is mainly down to the adaptive response that has been mounted. Adaptive immunity is based on the special properties of the lymphocytes, both B and T cells, and these respond selectively to non-self, to pathogens. And I want you to think of the lymphocytes as being like a key and the pathogen as being like a lock. Each lymphocyte will be useful against one pathogen. However, once a lymphocyte has been activated against its pathogen, the lymphocyte creates copies of itself. Sometimes the adaptive system works independently, but much more often it works in conjunction with innate cells. Adaptive immunity can be further categorized into humoral mediated or cell mediated. We also call humoral mediated antibody mediated. So in humoral or antibody mediated, B cells will secrete antibodies that bind directly to extracellular antigens, i.e. antigens that are outside of the cell. And this stops the antigen from entering the cell by attracting complement proteins, and the complement proteins will lyse the pathogen, i.e. it deflates the pathogen, it bursts a hole in it essentially. Or it can actually attract other cells that will phagocytose the antigen. Whilst in cellular immunity, macrophages and dendritic cells will present parts of the antigen to the T cells. And it's important to note that these are antigens inside the cell, intracellular antigens. The T cell will secrete messenger molecules that I already described, cytokines, and these alert a different form of T cell, known as cytotoxic T cell. These then destroy the macrophage or dendritic cell, and of course the pathogen that's present inside it. We can categorize adaptive or acquired immunity as passive or active. Active immunity refers to the process of exposing the body to an antigen to generate an adaptive immune response. The response usually takes days to weeks to develop, but may be long lasting, and we can further classify active as either natural or artificial. An example of a natural active immunity is encountering a hepatitis A virus and becoming infected with it. The subsequent recovery will give rise to memory B and T cells, which will confer a lifelong protection from hepatitis A. An example of an artificial active immunity is a vaccine. A hepatitis A vaccination will generate memory B and T cells that will lay dormant until the exposure to the hepatitis A virus in the wild. The length of the protection from a hepatitis A vaccine is usually around 25 years or slightly less than that. So moving on to passive immunity, this refers to the process of providing antibodies, typically IgG, to protect against infection. This has an immediate but relatively short-lived effect. Once again, we can separate this into either natural or artificial. An example of a natural passive immunity is the transfer of maternal antibodies across the placenta to a fetus. An example of an artificial passive immunity is the use of a serum from people that have antibodies directed against a pathogen. So for example, with snake venom, they would recruit people that have been bitten by a snake and successfully recovered. They would then remove blood from this person, isolate the antibodies directed against the snake venom, pull all of these antibodies from different people together, and then provide them antibodies to someone who needs them, i.e. someone who's been bitten by a snake. So we briefly mentioned vaccines on the last slide, so I wanted to provide you with a little bit more information on them. Vaccination is the most effective way of controlling infectious diseases. Vaccines contain immune cell mitogens, and these are compounds that deliberately stimulate an immune response to the particular pathogen. Vaccination programs have been largely successful and have resulted in the eradication of some diseases, including of course smallpox. So moving on to the organs that are associated with the immune system, as you can see there are quite a few of them. So firstly I wanted to direct your attention to the primary organs, and these include the thymus and the bone marrow. As previously stated, the bone marrow is where hematopoiesis occurs, and the reason that the thymus is a primary organ is because this is where T cells are matured. So the remaining organs are secondary organs, and they play a role in storage and transport of immune cells. And the secondary organs include the tonsils and adenoids, lymph nodes, lymphatic vessels, spleen and Peyer's patches, the appendix as well. I think we have maybe 3 sets of lymph nodes on this diagram. In actual fact, the human body contains between 600 and 700 lymph nodes. Similarly, we have a group of 4 Peyer's patches here. Peyer's patches exist throughout the entire GI tract, and there are many hundred of them. So the diagram isn't all that accurate. So the bone marrow provides an ideal environment in which stem cells can grow and develop. The bone marrow is composed of stromal cells and a microvascular network. And the reason that this provides an ideal environment for stem cells is because stromal cells will secrete extracellular molecules such as collagen, fibronectin, hemionectin, laminin, and growth factors, and all of these are essential for stem cells to grow, divide, differentiate, and ultimately they'll result in a stem cell becoming a mature blood cell. So the majority of our lymphocytes are actually not found in the circulating blood, as I mentioned before, but rather they're concentrated in lymphoid tissues, and only about 2% of total lymphocytes are found in the blood, and most of these are naive lymphocytes. The lymph nodes is where you'll find the highest concentration, with about 40% of our lymphocytes residing there, whilst the remaining lymphocytes are found in the spleen, the bone marrow, intestines, and some other minor tissues. So I've included a link to a video that describes the lymphatic system. If you need a refresher on this, then this is a great video to watch. I'd recommend you all glance over it when the lecture is finished. But I'll provide you with some information on the lymphatic system. So in brief, the lymphatic system is quite similar to the circulatory system. If you think of the blood vessels as being similar to roads that lead all over the body, distributing blood, then the lymphatic system is similar to the pavements in that they operate parallel from each other. There is a crossover between the blood vessels and the lymphatic system because the lymphatic system returns fluid to the blood. But blood vessels are actually porous, as hopefully you can see in this diagram here. And they will release water into the interstitial space, the space surrounding the blood vessels. And the lymphatic system will collect and return it back to the blood vessels. So the liquid flowing through the lymphatic system is known as lymph. The lymphatic system will also pick up antigen-presenting cells, which I've described before are immune cells that contain a foreign antigen. The antigen-presenting cells are transported to lymph nodes where they're introduced to our lymphocytes, and the lymphocytes are then activated, and in the same way that the lymphatic system takes macrophages and dendritic cells from the blood to the lymph nodes, they'll also return them back to the blood as well. So on screen now is a diagram showing the anatomy of the lymph node. The vessels that bring the lymph into the lymph node are called our efferent lymphatic vessels. Hopefully you can see them here. There's 3 of them shown on screen. Whilst the vessels that transport lymph out of the lymph node is called the efferent lymphatic vessel. And notice the slight difference in spelling between these two. So within the lymph node we have a germinal center, which we also know as the cortex. And this is where the B cells reside. We also have the medulla, and you'll find plenty of macrophages in there. The remaining space is called the paracortex, and that's where you'll find the T cells. So lymph enters through here, hopefully you can see my pointer, and it must first pass through the medulla in order to exit. And the macrophages that are present within the medulla will examine the lymph for pathogens, and if there are pathogens present, the macrophages will phagocytose them and present them on their surface to the T cells in the paracortex. Okay, so moving on to the spleen. The spleen is located on the left-hand side of your body, behind the rib cage, right at the bottom of your ribs on the left-hand side. Within the spleen, we have an area called the periarteriolar lymphatic sheath, also known as the pals. You can see it here in a light grey colour. And this contains the T cells. The T cells are in the pals area. But it also has macrophages as well. And surrounding the pals is the marginal zone. And this is an area rich in macrophages as well. So the marginal zone and the pals contain macrophages. So the germinal centre, also referred to the follicles, contains B cells. Together, the pals, the marginal zone, and the germinal centre is known as the white pulp because it's so rich in white blood cells or immune cells. The white pulp is essentially has the same function as a lymph node. It collects antigens and it destroys them. Surrounding the white pulp is an area known as the red pulp, and its function is to dispose of old, damaged red blood cells, and it's obviously called the red pulp because it's so rich in red blood cells. The gut-associated lymphoid tissues are a series of lymphoid tissues along the GI tract. These include the tonsils, the adenoids, the appendix, and the Peyer's patches. In terms of morphology, all of these sites are unique, but they have one commonality: the presence of specialist epithelial cells known as M cells. And these are cells that collect antigen from the epithelial surface of the GI tract and pass them on to the lymphocytes. Okay, so the remaining slides of the lectures of this PowerPoint are for your benefit. They're for you to study as a guide, and I recommend that you create a glossary for yourself. This is the beginning of a glossary, but you should keep this glossary near yourself when you're completing assignments or studying. And again, something that you will need in the glossary is a key to what the main differences between the innate and the adaptive system are, and this is the beginning of that for you. So before you move on to the next tutorials, I'd recommend you watch some of these videos as well, and this will give you a head start before the tutorials begin. Okay, thank you.